Good morning to all of you. So today we will discuss a case of a microcanonical ensemble, and I am going to take a case study of a classical ideal gas. At fixed number of particles, volume and energy. So the case study is that of a classical ideal gas. Okay. So when I say an ideal gas, this is an example of a system with degrees of freedom that are continuous. Okay. So if I take a gas inside a box of volume V and there are n particles in this box at the total energy E. So these particles here basically are free to move anywhere in the box and their momentas are also continuously varying. So I can say that a particular microstate that I have shown here, let us say this is a microstate mu1, okay, of the macrostate NVE, then it is basically a set of these coordinates Ri. I can take the coordinates as position coordinates as Qi and momentum coordinates as Pi. So Q and P are continuous random variables, and so this is a system with degrees of freedom that are continuous. So I can also take, for example, the same macrostate NVE for a different arrangement of particles. Okay. Let us call it as mu2, and this way I can construct a large number of microstates, very large number, all corresponding to let us say a very large number m, all corresponding to macrostate NVE. Okay. So all microstates correspond to the same macrostate NVE, the specified values of N, V and E. So which brings us to the next question: what is the probability of finding my system in any jth microstate? Well, that is of course 1 upon the total number of microstates accessible to my system at the specified conditions of N, V and E, because all microstates are equiprobable. Okay, by the Boltzmann's assumption. So if there are omega number of microstates and all of them are equiprobable, the probability of getting my system in one of these microstates is certainly 1 upon omega. Okay. Now I must compute omega, because that is how I will develop thermodynamics of the system. Okay. Because once I compute omega, I can do a lot of things. I can compute entropy by taking a logarithm of this omega. From entropy I can compute energy, chemical potential, pressure, so on and so forth. All thermodynamic quantities can be computed once I have in my hand the expression for entropy by invoking derivatives of appropriate type, which means for any thermodynamic calculation to perform, I must first compute the number of microstates, because that is how I connect statistical mechanics with thermodynamics in the system. So to compute the number of microstates, you need to understand the following. we can think of our system to be having an energy and I am calling the energy of the system as the Hamiltonian. Let us pick up any Hamiltonian, any microstate mu of j, and we say that the energy of the system, which is basically the Hamiltonian, is not exactly constrained to be E, but is allowed to vary between E plus delta E and E minus delta E. So, as you can see already there is some relaxation of the constraint that the energy has to be strictly E, and I will show you why this relaxation was necessary, because it allows me to compute the number of states in the following way. Now, if you are worried about the fact that I have taken a small spread delta E, it poses no problem. It poses no problem because I can take delta E to be so small that the ratio of delta E over the actual energy of the system is a very small number. So, it is like almost a constant energy surface. The width is so small that the ratio of width over energy is essentially 0 or a very smaller and a number much smaller than 1. This small relaxation of a spherical surface to a spherical shell allows me to compute omega as the accessible phase space volume divided by some resolution. Now, what is the meaning of accessible phase space volume and resolution? Well, you can think of the following. Our system has access to, is basically it can be represented as a single point in a 6n dimensional phase space. So, I am going to draw a phase space here. Okay, so I am going to draw a phase space, and this is a 6n dimensional phase space. So, basically what I have done here is I have taken momentum and I have taken 3n momentum axis, and I have taken positions, and I have taken 3n position axis. Because I have a 2-dimensional surface, I am constrained to show only 2 axes here, but you must imagine 3n momentum axis and 3n position axis, and in this 6n dimensional phase space my entire system of n particles is represented by one point, okay, which means if I project my point here on some axis p of I, okay, so if it is projected on pi, so basically what I get is the momenta of the ith particle. Okay. And similarly, if I project it on the q axis, then it gives me momenta of the ith particle. This will give me momenta of the ith particle. Okay. Suppose I project this point on px of 5th particle, it will give me the x component of momentum of the 5th particle in the system. So, what I can do here is compute the accessible phase space volume to my system and divide it by the smallest compartment in the phase space, accessible to my system. So, I can divide this phase space into small cells, okay, and these cells here are to be you can do this construction of this phase space in you know as a net of cells of the size, okay. So, the phase space here is to be seen as you know cells of size h to the power 3n. Okay. So, the smallest compartment in the phase space has a size h to the power 3n, but simple reason being the for a single particle the momenta and the position are uncertain by an order h. Now, this is in one direction. In 3 directions you will be uncertain by of this product by an amount h cube. For n particles the system point in the phase space is uncertain by an amount h cube to the power n, which is basically h to the power 3n. So, this is the smallest resolution or this is the highest resolution you have in this phase space. So, you can think of the phase space volume as integral over all the position coordinates and integral over all the momentum coordinates subject to the constraint that each position coordinate was inside the volume V and the momentum coordinates are constrained to have a sum of squares between twice m E minus delta E and twice m E plus delta E. Okay. So, that is my numerator and the resolution which is basically the smallest cell in my phase space is h to the power 3n. Okay. Now, if you integrate the position degrees of freedom, each position degree of freedom will give me a volume V because that is the integration of dq I. There are n such position integrals, so this gives me V raised to n and this is multiplied to the leftover which is these momentum integrals 3n of them, actually this is going up to 3n. Okay. So, okay, subject to the constraint that my sum of squares of momentum is between divided by h to the power 3n. Okay. In fact, I am going to write down this h to the power 3n here. Okay. What I have done here is just the fact that an integral triple integral of this type is basically volume V. Okay. And there were 3n such integrals, it has given me V to the power n. Okay. So, this is what I have used here and now this is giving me the number of states accessible to my system at the macro state NBE. So, let us call this as equation 1. Okay. So, I am going to refer to this integral momentum integral as omega p. okay, omega p, and I am going to define it as so I am going to write down let me call this as omega, which is my total number of states, as v raised to n upon h to the power 3 n into omega p, and I am going to call this as equation 1, where this omega p is just the contribution to omega coming from this momentum spherical shell in 3n dimensions. Okay. Again, the constraint is that the sum of squares of these momentum degrees of freedom is constrained to be lying between the values twice m e minus delta e there is going to be 3 n here. Okay. So, you could think of it the following way. So, this is like you can think of a momentum spherical surface, okay, at a radius r, which is nothing but square root of twice m e, okay, and I have called that the radius is square root to twice m e because the equation of a spherical surface is summation over I going from 1 to 3 n p I square equals to r square. This is the equation of the spherical surface, and I know this is equal to twice m e. This is the equation of a spherical surface in 3 n dimensions. So, I can take one more spherical surface at radius r2, which is at square root of twice m e plus delta e. Okay. So, let me write to sort of save the space, I am going to write it because I have little space available here. This is a spherical surface at radius square root of twice m e. I am going to write down another spherical surface at radius twice m e plus delta e, and I am going to write down an inner spherical surface with radius r1 equal to square root of twice m e minus delta e. So, these are the 3 spherical surfaces I have taken, and the width of this shell I am calling it as delta r. Okay. Remember, this is the shell that I have taken in the beginning. This shell corresponds to, and what I have taken here is a shell of twice delta E. Okay. So, it is a reminder that I have already taken a shell of thickness twice delta E that simply corresponds to this thickness delta r. Okay. So, this surface is at E plus delta E, and the innermost is for E minus delta E. Now, clearly I can write down this omega p as, because it is a spherical shell volume, okay, as some kind of a solid angle 3n dimensional solid angle. Some kind of a solid angle. I am going to refer solid angle by an expression, a symbol theta. Let us say theta is the solid angle, and just to remind that this is a 3n dimensional solid angle, I am going to raise just put a superscript 3n, or let us say, since it is a label, let us use a subscript so that you do not confuse it as a power. So, this is a 3n dimensional solid angle multiplied to the radius to the power 3n minus 1 into thickness, which is delta r. Now, this is very easy, because if you had taken a sphere in a sphere in 3 dimensions, let us say in 3 dimensions, if you had taken a sphere of radius r and you were asked to compute the volume of a spherical shell at radius r and of thickness dr, well, you could have computed the volume, this shaded region, as simply 4 pi r square, which is 3 minus 1, into delta r. This was the volume of the shell. Okay. So, this 4 pi that you have taken is basically the 3D solid angle into r raised to 3 minus 1, 3 is basically the number of dimensions, into delta r. That is what I have done here. We have, instead of a 3 dimensional momentum shell, I have a 3n dimensional momentum shell, which means instead of 4 pi I have to take a solid angle which is 3n dimensional, that is this guy, and instead of r to the power 3 minus 1 I have taken r to the power 3n minus 1, because now the number of dimension is 3n, that is the second guy, and the thickness that I have taken is delta r, which is this guy. Okay. So, I am going to compute each of them separately. Okay. So, let us label this as some equation 2, and now proceed. The easiest thing to compute first is delta r, thickness of the 3n dimensional shell. Now, this is nothing but r2 minus r1. If you look at the figure, r2 is the outermost, rn is the innermost. So, the thickness delta r is r2 minus r1, which is nothing but I will take the prefactor square root of 2m as common and write it as e plus delta e square root minus e minus delta e square root. I am going to take square root e also outside, and this will give me simply 1 plus delta e by e square root minus 1 minus delta e by e square root. This is where approximation will come to our rescue. I have already taken e to be very large and delta e to be small. If you recall your observation here or your assumption here, I am going to, so delta e by e is already taken to be much smaller than 1, which means if I expand it in a Taylor series and I retain terms of only first order, then this expansion straight away gives me each one of these terms inside the square bracket as a Taylor expansion. So, to linear order I can write it as delta e over twice e, and I am going to drop terms of the order delta e square minus, here I will get 1 minus delta e by 2 e, again I am going to drop terms of the order delta e square here. So, this is basically just twice m e square root into delta e by e, which is nothing but twice m by e square root into delta e. okay, because delta E over E is much smaller than 1. So, I will not be taking terms beyond order 1 in delta E. So, delta R is computed very simple. So, let us plug this delta R in equation 2. What we get now is omega p as the 3 dimensional solid angle into r to the power 3n minus 1 into delta r, which is already computed, twice m by e square root into delta E, and let us plug the value of r also. R, as we already know, is square root of 2m by e, 2m e. So, I can write this as I can simply write it as 2m e to the power 3n minus 1 the whole divided by 2 into 2m by e to the power half into delta E, since I have used r as square root of 2m e. Okay. Let us call this as equation 3. Now, you can see that the only thing remaining is to compute the 3 dimensional solid angle, okay, that is the only thing remaining. So, here we take a small digression. A small digression is needed here. I am going to compute a different integral, okay, disconnected from our problem. So, take some integral, this is a pure mathematical construction, okay, I, which is nothing but the n dimensional integral or sorry 3n dimensional integral of this Gaussian. Okay, so I have got a Gaussian integral, an n dimensional. Now, since all these momentas are independent, I can write it as simply this integral is between minus infinity to plus infinity. Each integral on each degree of freedom pi goes from minus infinity to plus infinity, and there were 3n of them, and since each degree of freedom is independent of the other, I can write it as a single integral going from minus infinity to plus infinity of some variable p. It is a dummy variable because you have a definite integral here, e to the power minus p square, the entire thing raised to power 3n, and you know the guy inside the bracket, this is nothing but square root of pi to the power 3n, because I know that the Gaussian integral is square root of pi. So, I am going to write it as pi to the power 3n by 2. So, I have just computed this integral I as which was defined as these n integrals of okay, this is a product, okay, this is a summation, this is not a symbol pi, this is a product of dpi e to the power minus summation over all I going from 1 to 3n pi square, and we have just computed this result as pi to the power 3n by 2. Okay. I am going to rewrite this integral because using the fact, I am going to rewrite this integral using the fact that this volume element, okay, is nothing but the 3-dimensional solid angle into my summation over pi square into dr or d. Okay, so this is basically I have to define what is the meaning of this r here. R here is nothing but square root of summation I going from 1 to 3n pi square, okay, because summation overall pi square is nothing but r square, okay. So this is because if you have a if you have in just 3 dimensions, okay. So I am just going to show in 3 dimensions dp1, dp2 and dp3 is the volume element. I can write it as 4 pi p square, which is nothing but p1 square plus p2 square plus p3 square into dp, where p is nothing but square root of sum of p square, okay. So that is what I have written. This 4 pi is nothing but 3D solid angle. So instead of 4 pi I have taken our 3n dimensional solid angle, which is this term. Instead of just p1 square, p2 square and p3 square, I have taken summation over all pi square, which is nothing but my r square. So this is nothing but theta to the power 3n into r square into dr, okay. So I can now write down my integral I as, which is already calculated to be as pi raised to 3n by 2, but now I am going to rewrite my integral as simply instead of individual coordinates going from minus infinity to plus infinity, I have taken now the magnitude which is r. Now r can only go, the radius can only go from 0 to infinity, okay. For example, analogy with 3 dimensions would be if I take this volume element and some function of p, this integral, if I make p1, p2, p3 all go from minus infinity to plus infinity, I can rewrite this as r going from 0 to infinity 4 pi r square dr into f of p, okay, where r square is nothing but p1 square plus p2 square plus p3 square, okay. So in the same analogy I am going to write down this as okay. So I am going to use as a the analogy with 3 dimensions. So our integral now becomes theta to the theta 3n, 3 dimensional solid angle into r square, and this function now, our function e raised to minus r square into dr, fine, because we are integrating this I, where e raised to minus summation pi square is simply e raised to minus r square, right. So now I can substitute r square as some u, okay. So this will give me twice r dr as du, and which will finally give me my dr as 1 upon 2 into square root of u du, correct. So, I am going to substitute this in my integral, which is already pre-computed to be pi to the power 3 n by 2, but now this will transform to an integral in u, where the limits on u will go as usual from 0 to infinity. Theta 3n dimensional solid angle, r square is already taken as u, and e to the power minus u, and dr is taken as 1 upon 2 square root of u du. Okay, so let me just check everything here. Okay, so I have made a small error here. So, just a small correction here, this cannot be r square, it has to be r to the power 3 n minus 1. Okay. So, this has to be basically 3 n minus 1 by 2. Okay, because in 3 dimensions you have to take 4 pi r square dr, okay, which is r to the power 3 minus 1. So, in 3 n dimensions you have to take the radius to the power of 3 n minus 1. Now, radius itself is summation pi square raised to 1 half, okay, as I have written here. This is my radius, okay. So, r to the power 3 n minus 1 would just be this summation I pi square to the power yeah. So, this is already 3 n minus 1 by 2, that square root is 1 by 2, okay, correct. So, with this small error, this becomes three n minus 1, and here this becomes u to the power okay. So, then this becomes I can write down pi to the power 3 n by 2 equals to this solid angle is a constant. This simply becomes integral 0 to infinity. In fact, I can take 1 by 2 also outside. This simply becomes u to the power 3 n by 2 minus 1 into e raised to minus u du, and this is nothing but the definition of 3 n by 2 minus 1 factorial. So, this gives me nothing but 3 n by 2 minus 1 factorial, where I have used this result integral 0 to infinity some u to the power n e raised to minus u du is nothing but n factorial. Okay. So, I can now compute my 3 n dimensional solid angle as simply pi raised to 3 n by 2 into 2 divided by 3 n by 2 minus 1 factorial. So, let us call this as equation number 4, and you plug this in our equation 3, and that will give you the enumeration of omega or enumeration of microstates. So, our omega p omega number of microstates for our system simply becomes so our equation 3, if you see, in fact I am going to plug it in equation 1. Okay. So, this is to basically to get the final answer. So, I am going to write it as we are going to plug it in equation 3 and using then in equation 1. Okay, finally, we want the omega. So, this we had v to the power n upon h to the power 3 n into the component coming from momentum space, for which we have just computed the solid angle, that is 2 pi to the power 3 n by 2 divided by 3 n by 2 minus 1. Okay. And this component 2 m e to the power 3 n minus 1 by 2 into, let us see if something else is pending, into square root of 2 m by e into delta e. Fine. Okay. So, this is the final form of the entropy of the number of states, but there is still a problem here. So, this problem is basically due to the fact that we have seriously overcounted the number of microstates. I will explain why do we need to correct this. The fact that we have taken a microstate mu 1, which is basically particles arranged like this. So, I am going to show only 3 particles to make the case simple. So, I will take the first particle here, second particle here and the third particle here. What you have just computed also includes a microstate precisely with the same arrangement, but particle 2 here, particle 1 here and particle 3 here, without changing the location of 1 to relative orientation. I can just permute these labels 1 2 3 in 3 factorial ways. So, this is basically there are 3 factorial microstates for just 3 relative orientations of 1 2 and 3. Now, with n particles, clearly there are n factorial microstates that are overcounted. Okay. So, I can say that I must correct this overcounting, okay, because the particles are indistinguishable, since n particles are identical, okay, we need to compute the omega number of states by removing all those n factorial permutations that you can do on these n particles. So, our final expression is just this expression that we have computed, and I want to correct it for overcounting by simply taking, you know, by simply dividing it by n factorial. Okay. So, this n factorial is very necessary, and I am going to just remind the user that what we have done here by simply a highlighted correction. Okay. So, this n factorial is a correction necessary to remove the overcounting of the microstates, because precisely for n particles I can shuffle the positions without changing the relative orientations or relative positions in n factorial ways. So, each microstate that was computed in omega was basically overcounted by a factor which is n factorial. So, I have to correct for that, and now I have a correct expression for omega. So, this is the root. So, this ends the, you know, or this ends the discussion on computation of microstates, but it also opens up the route to thermodynamics. And the route to thermodynamics is opened up by simply computing entropy by taking the logarithm of omega, okay, by Boltzmann's formula, and I can simply write down, take the logarithm using the fact that n is large. Okay. So, I can approximate 3n by 2 minus 1 as 3n by 2, and write down the entropy as n ln V minus n ln n factorial plus n minus 3n ln h, okay, but I can write it as minus 3n by 2 ln h square and plus ln 2 plus 3n by 2 ln pi plus 3n by 2, I am going to write down 3n minus 1 by 2 as just 3n by 2 into ln 2 m e minus 3n by 2 ln 3n by 2 plus 3n by 2 plus 1/2 ln 2m by e plus ln delta e. Okay, now there are several terms which can be dropped because they are of lesser order, much lesser order than the other terms. So, clearly I can drop this term because it is of the order ln e. This term also can be dropped, and I am going to drop this as well, okay, because these quantities are intensive and they are not going as extensive, going as n or n ln n. Okay. So, what I get here is just then the following. So, I can write it as well, the entire thing is multiplied by kb. So, this is nothing but if I take n kb as constant, n kb as a constant prefactor, and this just nothing gives nothing but v by, if you rearrange the terms you can write it as ev by n into 4 pi m e e by 3 n h square. To the power 3 by 2. So, this is the definition of entropy, and in the next class we will compute other various thermodynamic quantities starting from this expression for entropy. So, we will break here and we meet in the next class.